Okay, what I want to do first thing today is go over the quiz that I gave you yesterday. So let's start with that, or primarily because you should be able to use it to determine if you want to stay in here or not. Maybe it would be best for you not to stay in here, and that was the purpose of the test. Okay. Let's see. The stuff that was on this quiz is stuff that 2 weeks from now it should take you no more than 10 minutes to do. Okay, this is supposed to be easy. Okay, let's look at the first thing. First of all, distribution function. If x is a random variable, every random variable has a distribution function. A distribution function, f of x, is always defined to be the probability that the random variable is less than or equal to a particular value. That's the definition of a distribution function. Okay, so the first part of the test, part A, note you just simply plug in 2.5 into that formula, so the probability is going to simply be 2.5 minus 2 squared is equal to a half squared, which is equal to a quarter. So that's the answer to the first part A. Part B, if you have a continuous distribution function, now if you have a random variable that's continuous, the cumulative distribution function will be continuous. If you have a random variable that's discrete, the cumulative distribution function is going to be a step function. So it'll be discrete, right? A discrete is going to look something like this. Okay. If it's continuous random variable, it will always be continuous. The CDF, or the distribution function, will always be continuous. And who are you? Who are you? Were you here on Monday?
No.
Did you sign up for the course? You're not auditing. You're actually taking it. What happened on Monday? Okay. First rule is, Ben McCloskey is the TA. You can't sit behind him. Okay. Index card. Here's the course outline. Here's the test. 1-0 already in the course, since you missed the quiz. And I'm going over the quiz now. Distribution. If your random variable is continuous, then the distribution function will always be continuous. If a random variable is continuous, then the value that the random variable is equal to a specific value is always 0. So part B, the answer is 0. Okay. Part C, notice that the random variable is never above 3. So part C is actually equal to 1 minus the probability that x is less than or equal to 2.5. I'm sorry, that should be simply less than 2.5. Of course, if it's continuous, it doesn't matter if you have less than or these are the same quantity things, whether it's less than or less than or equal to. Same difference as long as it's continuous. So that's equal to 1 minus a quarter. Okay. D, that's the derivative. The PDF is always a derivative of a CDF. So PDF is going to be 2 times x minus 1 if 2 is less than x is less than 3, 0 otherwise. Okay. Let's see, part 2. How do I get? Interarrival time has an exponential distribution with a mean 10. We're going to talk more about this on Monday. The 2 distributions you must memorize, the exponential and the Poisson. They're extremely important. I'll talk more about them on Monday. The exponential distribution looks like this, 1 minus e to the minus lambda x. If x is greater than 0, 0 if x is less than or equal to 0. Lambda is the mean rate, or the mean time, the expected value of x is equal to 1 over lambda. So the answer to this, if you let your units be in terms of minutes, the answer to this, for this problem, is 1 minus e to the minus 1/10 x, if x is greater than 0, 0 otherwise. Okay, this is not something you can figure out. You just have to have memorized it. Exponential is really important. So this is just something you're going to have to memorize. The main reason is a lot of arrival processes have an inter-arrival time that are exponential. So we'll be using that a lot. Okay? If you have an arrival process where the number of arrivals per unit time is Poisson, then the inter-arrival time is exponential. And in fact, if the inter-arrival times, if you get 6 calls per hour, on the average, how many minutes do you have between calls? 10, that's right. Right? If you have 6 calls per hour, you're going to have approximately, on the average, 10 minutes between arrivals. So the answer to this problem is exactly the same as number 2, because it's exponential with an average inter-arrival time of 10. Okay, so answers 2 and 3 are the same. 4, uniform, that should be something that's pretty straightforward. The uniform distribution, the distribution function always looks like a straight line between 2 points. If it's uniform between A and B, the distribution function always looks like this. Now, a couple of you had the distribution function looking like a rectangle. That's not the distribution function. What is that? PDF, right. The PDF for uniform is a rectangle. Distribution function's a ramp. Okay, again, that's not something you can figure out. You either have memorized it or not. And it just, I guess this one is not quite as important as the exponential, but it's so easy, you might as well have memorized it. So the answer actually to part 4 is going to be something like this. F of x is equal to, it'll be 0, between 10 and 20 minutes, so less than 10. It's equal to x minus 10 over 10 if 10 is less than x is less than 20. And it's equal to 1 if x is greater than or equal to 20. Okay. How do you interpret now that I've gone through this? You got the quiz in front of you. Several of you missed everything on the quiz. So what do you do with it? Okay. If your reaction to this was, oh gee, I should have known that. If you'd have told me a couple days ahead of time I was going to do this, I'd have gotten it right. If I could have reviewed my statistics book, this would have been easy. If that's your attitude, then there's no problem. If after looking at this you think, man, that's confusing, where do you get that stuff? Then you need to drop the course and take a statistics course. If by hindsight this stuff looks not trivial, then you need to take a statistics course before you take the simulation. Okay. Now, the concept of the exponential and Poisson, I'm going to spend some time talking about that on Monday. So if that's not clear to you, that's okay. I'm going to try to clear that up on Monday. You may not have had that in a previous course, and that's okay. But the previous course should have at least covered what the distribution for exponential was and covered what the distribution for Poisson random variable is. Okay, so that's kind of the way I use this for. It's really the purpose of this is for your own diagnostics, so you can figure out if you should stay here or take it next year. Okay, any questions? Okay, let's talk about simulation. What I want to do is go through today an example that you're going to do yourself in lab on Friday. So basically my purpose the rest of today is to prepare you for Friday's lab. Let me give you the problem first. Okay, what I want to do is go through a simulation by hand. Excuse me. Okay, so we're going to do a really simple simulation. In fact, it could be kind of boring. But the fact of the matter is simulation is actually very easy. The conceptual framework for simulation is as simple as this example. Okay. There's programming details that kind of get complicated, but the concept of simulation is really straightforward and really easy. And going through this example, although it might be kind of boring, we'll come back to it and talk about it because it really contains several of the key parts to simulation. Okay, so what am I going to do? All I'm going to do is simulate a simple single server queuing system. So we're going to have some sort of server and a queue. If you haven't had queuing theory before, that's okay. A queue is a waiting line, right? So we just have a waiting line. So we're going to have arrivals coming to this. They're going to go into one server, and then they'll queue behind the server if they have to. Okay. What we're going to do is we're going to have arrivals coming every 12 minutes. Okay, so every 12 minutes an arrival is going to come. And then there's going to be a service. The service is random. So let's say the service time, we're going to do it something like this. Service time is, we'll say that's a random variable S. Okay. The probability S is equal to some value X is as following. It's equal to 25% if X is equal to 10. It's equal to 50% if X is equal to 11. It's equal to 25% if X is equal to 13. Okay, so that's our distribution for service time. I guess one thing I didn't really talk about on Monday that I should have was what do we mean by simulation? Because simulation means different things to different people. Right? An airline pilot is going to think of simulation as being a mock-up cockpit in which he can fly an airplane without leaving the ground. A chemical engineer would think of a simulation as a, in civil engineering they're worried about chemicals flowing through pipes, fluids flowing through pipes and whatever. which is extremely hard to mathematically describe. So to them, a simulation is a deterministic evaluation of a whole bunch of differential equations that describe fluids flowing through pipes or a refinery or whatever. A petroleum engineer is going to think of a simulation as, again, deterministic stuff where they're to try to describe a petroleum reservoir, an oil reservoir in the ground. That's really hard. So it's a bunch of differential equations, again, that describe this oil field that's below the surface. And that would be a simulation to a petroleum engineer. Okay. To an industrial engineer, a simulation is a way to evaluate stochastic processes. Okay, so we're always going to be describing something that has some random factor to it, because for our purposes, randomness is what messes things up. If you're a manufacturing facility, randomness is what causes difficulties in the manufacturing facility. If you're in charge of a railway, the fact that weather messes up the timing of the trains, that's what causes difficulty. Same thing in an airline, or in the service industry. If you're trying to decide how many policemen to have to cover a certain area, it's the randomness that makes things difficult. And so to an industrial engineer, it's the reproduction of that randomness that we're interested in. So when we talk about simulation, that's always what we refer to. Okay, so we're going to only have one simple source of randomness, and that's the service time. Okay, we're going to have to describe it somehow. We're going to do this by hand instead of on the computer, so we see what the steps are. So we're going to have randomness. I picked these probabilities so we can reproduce it easily. We're going to toss two coins. Okay, so if we come up with two tails, that's going to be a service time of 10. If we come up with two heads, we're going to have a service time of 13. Okay, so this is going to be either a head-tail or a tail-head. That'll be a service time 11. Okay? Well, that's what our process is going to be. Go ahead, and so that you can do it with me, why don't you pull up Excel? And we'll do this together. Okay. We're going to have, what I'm going to do is I'm going to create a chart and follow that chart down. So if you want, we're not really going to use Excel for too much. It gets, for me, the paper gets too big to write it on the board. I can't do it on the board because of, there's just not enough space on this little screen. So Excel will make it easier. But if you'd rather do it on a sheet of paper, I would suggest turn this paper landscape, and there might be enough columns. Let me see how many columns you need. We're going to have 12 columns. Okay. My column headings are going to be in 2 rows. So, I never said this on Monday either. We have a couple students in here that are not industrial engineering students. So you don't have accounts automatically. We can get you accounts. Ben, do you know how to get accounts? You just okay. I think we might have 2. Not in general. That's not a good idea. Okay. Is everybody else industrial engineering in here? I thought we had one other person that wasn't. Okay. Okay, I'm going to have the first two columns are going to be headings. So let me just give you the headings for now, and you can type them with me, and then we can go back and start filling things in. I'll explain the headings as we go along. The first heading is going to be clock, time. Okay. Within the simulation, not always, but almost always, maybe all of our examples, time is going to be the main thing. Probably most of y'all have heard about Monte Carlo simulation. Have you heard the term Monte Carlo? Okay. Monte Carlo simulation usually, not always, but usually refers to a simulation that does not involve time. For instance, if you have an integral that's really hard to compute, there's Monte Carlo schemes for evaluating an integral. Basically, you put points at random and then you fill in the little squares. That'd be a Monte Carlo integration where you create a lot of random points and then you evaluate the integral over those random points. There's lots of examples of Monte Carlo stuff. Usually a Monte Carlo simulation refers to a simulation that does not involve time. We will be doing a simulation that involves time on almost everything. Just for the heck of it, let me back up again. Do y'all know what a random variable is? Can anybody define a random variable for me? I'll give you a hint. A random variable is neither random nor is it a variable. Yeah. That's exactly right. Very good. A random variable is a mapping or a function from the sample space to the real numbers. Okay? That's a random variable function. Assigns numbers to outcomes. What's a stochastic process? Any idea what a stochastic process is? No guesses? Not quite. A stochastic process is related to Markov chains, right? Include what? Oh. Are you making it too hard? A stochastic process is a sequence of random variables. That's all a stochastic process is. Random variable is a function, assigns numbers to outcomes. Stochastic process is a sequence of random variables. For our purposes, the sequence will always be a time sequence. So that's why. So what we're simulating in here is stochastic processes. In particular, we're going to simulate today a queuing process. Yes? That depends. That's a good question. The question was, are the random variables independent or dependent? The simplest type of stochastic process to analyze, of course, is a sequence of independent random variables. That's the easiest type of stochastic process to analyze. From that, you get things like the law of large numbers, weak and strong law of large numbers, and all sorts of stuff. It's more interesting, of course, when there's dependency, and for the most part, our stochastic processes will have dependencies in them. Yes. Yes, almost always we'll be simulating dependent variables. Possibly, yes. Okay, I need to repeat the question for the distance learning students. I forgot. But the question is, can you make dependent variable? Say it again. Uh-huh. No. Okay, the question is, for the simulation, you take a sequence of dependent random variables. you have to make them independent in some sense in order to simulate them? And the answer is no. And that's what we'll do here. We'll see the dependency in this example. Okay, stochastic process, sequence of random variables. For our purposes, the sequence is usually, the parameter of the sequence is usually going to be time. Okay, so time's almost always involved. So in the simulation, we're going to have to keep track of a clock time. That's kind of the internal mechanism for describing the stochastic process. The next thing I'm going to record is an entity number. Let me describe that. The question is, how do you move time? Okay, we're going to be simulating a stochastic process, so we're simulating the time movement of things. Okay, how do you handle the clock? One way to do it, the simplest way to conceptually do it, speaking of the clock, okay, this simplest conceptual way to do it is to say, well, we're just going to move the clock up minute by minute. So we'll start at time 0, and then we'll see what happens at time 1, and then time 2, etc., and just keep moving the clock up a fixed amount every increment. And then what that means is we'll have to describe the system, everything that happens to that system in that minute change. Okay, that's one way to handle the clock. And in fact, when I first had simulation, back sometime in the, late 60s or early 70s, that's the way we did it. That's a really dumb way to do it. For the most part, maybe not always, but usually it is. What happens if nothing happens for hours on end? We're simulating, one of my projects is to simulate a insect infestation within a forest. Okay, so the question is, it turns out in pine forest, there's a pine bark beetle that kills millions and millions of dollars of damage to pine forests in the south. And so we're trying to describe the population dynamics of this insect. And so we're going to describe what happens to a pine forest kind of on a daily basis. Well, if I was incrementing my simulation clock minute by minute, but I don't have a better description than what happens day by day, you see, I've wasted a lot of time. I'm doing a lot of calculations that are kind of foolish. Or we could go the other extreme. Okay, we'll make the simulation move in days, and we might have something in which happens in minutes or seconds. So moving at fixed increments is not a good idea. So what we will do instead is keep track of future events. We're going to keep track of things that might change the system and jump the clock whenever we need to. In other words, we might move the clock 1 minute if I know an arrival is going to occur in a minute. But if nothing happens to the system for the next hour, I'm not going to simulate what happens minute by minute. I'm going to jump the simulation clock 1 full hour and then describe. Okay? So we have some sort of system, and what we're going to keep track of is events that occur to the system that force a change of state of the system. Okay, remember what we're doing, we're going to simulate a simple queuing system. So there's only 2 things that can happen. We'll have arrivals coming, and then at some point in time there's going to be a service completion. When arrival comes, the system is going to change because it's going to increase. When a service gets completed, the system is going to change because we're going to lose the number in the system. So those are the 2 things. So we're going to keep track of arrivals, and I'll keep track of that with the letter A, and service completions, I'll keep track with the letter C. Okay, and we're going to keep track of the future events. So we're going to have a list. For now, it's going to be a mental list because it's not too hard to keep track of. We're going to keep track of a mental list of all of the future events that might happen. Okay? The simulation, what we're going to do is look at entities. entities is a generic term in a simulation that refers to the things that move around the system. If I was simulating aircraft, my simulation might be the aircraft, the entities might be the aircraft. Or if I was interested in how do I assign pilots to the aircraft, my entity might be the pilots. Or if I was simulating the Panama Canal, my entities might be ships going through the canal. Or if I was really concerned with how many tugboats do I need in order to make an efficient operation, the entities might be the tugboats. Or if I'm simulating an airport, the entities might be the people coming into the airport. So it's who knows what an entity is. It's just generic. It depends on the system. So here we're going to simulate a queuing process in which widgets come into the system. They're going to be worked on and then going to leave the system. So the entities are the widgets coming into the system. Okay? And so what we're going to do is we're going to follow those entities through the system. Okay, so the next heading is going to be entity. Did I spell it right? Entity number. Oops. And event type. That's too long. Okay. Entity number and event type. I don't like the way this looks. Excuse me for a minute. I'm going to make everything in the center. Yeah, I like that better. Okay. The next column is going to be, in this case, it seems kind of trivial, but it'll set the stage for Friday. Enter. Normally I would call that enter arrival time, but that's too big of a word, so I'll just say enter arrive time. Column D is going to be next arrival time. Then what? Then I'm going to write to coin toss. Service time. Number and system. Depart time. Cycle time. Sum of departures. I'll just put depart. I'll explain these a little bit more fully when we get to them. The last two columns, I'm just going to put the headings. They're not going to make any sense, so I'll describe them later. I probably won't be able to describe them until Friday. I'm just going to put time, then X, time times number, sum of time, times number. Okay. The last two columns certainly won't make sense, but they will pretty soon. Okay. Okay. I'm going to kind of move that up so I can see the difference between my headings. I made that a little bit small. That's the only reason. So I'm going to start on A4. Okay. I'm going to say that our first arrival comes at time 0. Okay. So we're going to start our system by saying at time 0 an arrival comes, and then every 12 minutes after that an arrival is going to come. So we're going to start by looking at time 0. The idea of the simulation, actually all a simulation is a bunch of tables. Okay, and, well, I guess there are two things. There are a bunch of tables and a bunch of accumulators, because we have to collect statistics. Okay. Okay, we're going to keep one table in our mind, namely all future events. Okay. We're going to start, and so we're at time 0. That's going to be entity number 1. I'm going to put 1-A. It's entity number 1, and the event that is causing the clock to change is an arrival event. Okay. The first rule we need to remember is that whenever there's an arrival, the first thing that happens is the next arrival time is calculated. Whenever there's an arrival, the first thing that happens is the next in-arrival time, and therefore the next arrival time is calculated. Our inter-arrival time is always going to be 12 for this case, because we have arrivals every 12 minutes. So the next arrival time is 12. Okay. Now with every entity, we're going to associate with that entity, we're going to calculate a service time that goes along with that entity. Okay, so this entity has some random service time associated with it. So we need somebody that is relatively rich. Does anybody in here have 2 coins? We need somebody with 2 coins. Alberto's got 2 coins. Could you toss them, please? What do you have? Heads and tails? Okay, so we have a 2 coin toss. We will put down head, tail. So that's our random number generator. All right, column E is a random number generator. Based on that, what's our service time for this entity? How many? 11, okay. I've already erased it and I don't remember. Okay, so this entities have a service. Okay, as soon as an entity comes, time 0, the number in the system goes up, so that's what we're going to keep track of. Okay, and we know that entity immediately goes into the queue. We've calculated how long it's going to be in the server, so it's going to depart at time 11. Okay, we now have 2 future events. Remember, we're going to keep track of our future events list in our head. We have 2 future events. One future event is going to occur at time 12. We calculated that. Right. Our future events are represented right here. Those are the times our future events are going to occur. Okay? So not only are we going to keep this in our mind, this future events list, we're going to automatically have to sort it. Because what we need to do is figure out what's the next event that's going to happen. So we go through our bubble sort routine, come up with 11. That's the next departure. Okay. So, by the way, everything else here this is all zeros. We don't need to do anything there yet. Okay. We've done everything we can at time 0. We have two events on the future events list. One that's going to occur at 11, one that's going to occur at 12. So we pull off the 11. So we're going to jump the clock to time 11. Okay. That's entity 1, and it is a service completion. So what is causing the clock to jump is an entity is the event service completion. Okay, so let's see. We only calculate inter-arrival time at an arrival, so these we don't have to worry about. Not much to do here. We're just going to record that it went down to 0. Okay, there is no departure. But we can figure out the cycle time for this entity. The cycle time was, if this entity left at time 11, it started at time 0, so the cycle time is 11. We've had, how come this didn't And what I'm going to keep in column J is the sum of all the departures. So we've had one customer departing. The columns K and L I'm not going to fill in today at all. We're going to come back to that on Friday. Okay. Now, there's how many entities on the future events list? 1. That's correct. There's 1 entity. Because there were 2, we pulled 1 off. Okay, so when do we jump our clock time to? 12. Okay, we go to 12. The entity that has done that is 2, and that's an arrival. Okay, what do we do at an arrival? Next arrival automatically. Okay, that's going to, the inter-arrival time is 12. So the next arrival is going to be 24. So this is basically creating entity number 3, and entity number 3 is placed on the future events list. Okay, so now we have a future event, entity number 3. Okay, this has a service associated with it. Okay, what time is it? 2 tails, you said? No, heads and tails. I can't remember what I said before, right? Okay, actually, I didn't hear you right. You probably said head, head. Okay, head, head. Good. Okay. So now we have a service time of 13. And the number in the system is 1. Okay. The departure time, what do I put for depart time? Yes, 25. Okay? The cycle time and the sum of departures, those are only calculated at a departure, at a service completion. We don't do that at an arrival, only at the service completion. So there's nothing more to do. Go back. Okay? So now we have to jump our clock time. Where do we jump the clock time to? To what? 24, that's correct. Okay? So at 24, this is entity 3 with an arrival. Next in-arrival time, 12. Next departure time, 36. Oh, 2 heads again, huh? Okay. Service time is 13. Number in the system is 2. We cannot calculate a departure time because this entity is in the queue. If you have think of a picture. Let's see if I can write a picture in here. Oops. Oh, wait. Looks like this. This is at time 13. No, 24. We're describing everything how the system looks after 24 time units. It's going to look like this. Okay. Now, because it's a simple system, you could actually look back and figure out departure time. But in a more complicated system, you won't be able to do that. So we will not calculate the departure time until we can do it easily. Okay. So we don't calculate the departure time until this entity goes into the server. Okay. That's when we will calculate the departure time. So it looks like this. We know this one's going to leave at time 25, and we know an arrival. So we still have only 2 entities on the future events chain. Okay. So let's see. Let me go back to this departure. We can't do that. So how do we move the clock time? Okay, 25. What entity is causing that to? Entity number 2. And that's a service completion. So we don't have to worry about inter-arrival time. We don't. do a coin toss, but our system does go down to 1. Okay? And at this point, we can calculate, okay, this entity leaves the server. The next entity goes into the server. So now we can calculate when that entity is going to depart. We have entity number 3 has gone into the server. The service time of entity number 3 was 13 minutes. Okay? So the departure time is going to be 13 plus 25. 38. Okay. The cycle time for the entity that is leaving, the entity is leaving at time 25. Entity number 2 came in at time 12. So that's 13. And we now have 2. Okay. Where do we move our clock time to? To where? 36. Okay. And this is a new entity. This is 4. An arrival, you always calculate the inter-arrival time. I'm running out of time. I guess we'll complete this on a Friday. I could probably complete this one row. Next arrival is 48. Coin toss. We'll do it legitimately. Go ahead and toss 2 coins. I'll actually do it down right this time. What? Oh, I thought somebody else did it. Two heads. Oh, well, that's interesting. All right. So, service time of 13. Number in the system is now 2. Don't have to worry about departure. Okay. So, that's the simulation. On Friday, you pretty much know everything you'll need to know for the Friday's lab, except how to fill in those last 2 columns. So we'll probably continue this just a little bit on Friday, then you'll be ready for the lab. Any questions other than the last 2 columns? Okay, you might save this because we're going to work with this. Well, I'll start at this point on Friday. So go ahead and save this, and then we'll pull it back up on Friday. Maybe I'll call mine first. I'll tell you what, if I will save this to the G drive. So if you can't save, no big deal. You can just get a copy of mine from the G drive, so it won't be any problem. On the G drive, let's see. Yeah, I really don't. I'll just call this first simulation. Okay. So you'll be able to access it on Friday. No questions? Okay, see you in lab. Remember, lab is in 301, not this room. Lab is in 301 at 8 o'clock.